Let's look again at the nuclear power plant secondary cooling loop that fails after a valve and pump fail. The secondary cooling loop removes heat from the reactor core to generate electricity and to stop the temperature from spiking, which would damage the pressure vessel and allow radioactive material to escape. If that happens, the reactor can never be used again, and the mess would take decades to manage. So when something goes wrong, it's vital to immediately stop generating heat. This is what graphite control rods are for. Control rods are part of the reactor protection system, or RPS, and pushing them into the reactor core stops the uranium reacting. But we're still in trouble because uranium is more complicated than a teenage love triangle. Uranium atoms have lots of protons and neutrons, and when a neutron smashes into its nucleus, uranium splits into two smaller atoms, krypton and barium, and 3 neutrons, which generates heat. These 3 neutrons now smash into more atoms, creating a nuclear chain reaction. Graphite control rods absorb neutrons and stop this reaction, but we still have a problem. One atom uranium splits into is called krypton-92 and has a nucleus with a total of 92 neutrons and protons. It has way more neutrons than protons, making it very unstable. Now, neutrons can change into a proton plus an electron and another particle called an electron antineutrino. This creates more heat in a process called beta decay. Now we have a rubidium-92 atom and a dangerously hot reactor core. Beta decay takes time. Krypton-92 takes around 1.84 seconds to decay to rubidium-92, which still has too many neutrons. So around 4.49 seconds later, it decays into strontium-92 with even more heat. Now, do you remember barium-141? That was the other atom that uranium split into. It also has too many neutrons. After around 18.5 minutes, it will decay to lanthanum-141. Strontium-92 decays to fermium-92 around 2.66 hours later, and lanthanum-141 decays to cerium-141 around 4.22 hours after that. Fermium-92 decays to zirconium-92 after another roughly 6.2 hours. I told you this lesson would make you fun at parties. Anyway, zirconium-92 now has 40 protons and 52 neutrons that are bonded tightly and won't decay anymore. If we started a stopwatch when we first inserted the graphite control rods, it would now be at around 6 hours. It takes another 33 days for most cerium-141 atoms to decay to praseodymium-141, and another 5 months after that for 99% of the remaining atoms to decay. Praseodymium-141 is stable, so it takes 6 months for heat to stop being generated. To deal with all this heat, we need what's called an emergency core cooling system, or ECCS, like this one, that pumps water through the heat exchanger into a water tank that will heat up, but buys us time for human intervention. Humans in operation rooms then try to understand what's wrong and gather information to help come up with a plan for post-accident heat removal, based on each unique scenario.